would like to introduce our remote presenter, Nikos Kostopoulos, who will be presenting Wi-Fi network monitoring with GÉANT WiFiMon. As an Internet 2 employee, I'm especially pleased to introduce someone who's representing GÉANT, who is our European counterparts and friends. Nikos is a PhD candidate at the National Technical University of Athens, Greece, and is a software developer for GÉANT WiFiMon, and is joining us remotely today from Athens. This is Nikos' first time presenting at ANOG, and it's a pleasure to have him speaking with us today. Welcome.
Hello, everyone. Thanks for the introduction. Sorry for not being there. I am Nikos. I will present to you WiFiMon, which is an official service of GÉANT, the European Academic Backbone. Next slide, please. Okay, I will start with the introduction of WiFiMon. Next slide, please. WiFiMon is a GÉANT service that monitors Wi-Fi performance as experienced by end users. The main idea is to provide the experience of network users that roam the Wi-Fi area and maybe in different locations. To do that, WiFiMon combines two types of measurements: crowdsourced measurements from end users and hardware probe measurements from devices which are placed in fixed points across the network. Optionally, if you want, in IEEE 802.1x networks, such as edge roam, you may correlate data from RADIUS and DHCP logs to provide richer analysis, for example, to document the throughput per access point across the Wi-Fi network. The main contribution of WiFiMon is that it aims to detect Wi-Fi throughput degradation and to determine underperforming areas within a Wi-Fi network. Our main goal is to provide some assistance to network administrators, for example, hints to enhance performance by installing more access points or taking some actions to check further WiFiMon configurations. Next slide, please. Okay, the first very important question is, what are the advantages of WiFiMon related to other monitoring tools? For example, the Ookla speed test, other Cisco solutions, or things like that. WiFiMon monitors the end user perspective. It monitors the end user experience, how end users, tablet users, mobile phone users, laptop users experience their Wi-Fi network. And the most important advantage of WiFiMon is that there are no requirements to install any applications or to intervene for the measurements. For example, users are not required to trigger a measurement themselves, but they do that automatically by visiting a website. I will explain more later. And finally, there is a centralized view of Wi-Fi performance available to the WiFiMon administrator. This will be clear by comparing WiFiMon with Ookla speed test. Next slide, please. The main differences with Ookla speed test is that by visiting the site, WiFiMon measurements are triggered automatically. Instead, in the very common tool Ookla, you have to press the button Go in order to trigger a measurement. The other advantage is that the results in Ookla speed test are collected by end users, and the Wi-Fi administrator takes no notice about these results. Next slide, please. Okay, here is an overview of the WiFiMon architecture. WiFiMon consists of four main components. WiFiMon Software Probes, or WSPs, is another fancy word, let's say, for the end user devices, laptops, tablets, devices that which are available to the end users themselves. WiFiMon Hardware Probes are devices which are placed in fixed points across the network and monitor Wi-Fi performance with the same technology as the technology used by the WiFiMon Software Probes. The two most important components of WiFiMon are the WiFiMon Analysis Server, which is a central collection point that collects all the measurements, stores them, processes them, correlates them optionally with additional information, and provides visualizations to the WiFiMon administrator, and the WiFiMon Test Server, which is the main component which is used to perform WiFiMon measurements. For example, the WiFiMon Software Probes or Hardware Probes trigger measurements against this component. The idea here that we can see in this figure is that we have to place some JavaScript lines. WiFiMon is based on JavaScript technology, So we have to place these lines in a frequently visited website, in the HTML code of a frequently visited website. For example, for a campus network, this can be the main site of the university, or for a conference, so for example, for Nano, it could be the agenda of the conference. And when the software probes or the hardware probes visit this website, some measurements are triggered automatically against the WiFiMon test server. Some small images or some garbage test data are downloaded or uploaded, and the end devices calculate the measurements, which can be download throughput, upload throughput, or other measures, and stream them towards the WiFiMon analysis server for further processing. Next slide, please. Next slide. Here I will delve more into the components of WiFiMon. As I said before, the WiFiMon server is responsible for holding the code and test data for performance measurements. It is based on JavaScript technology. Test data may be some small images which gradually increase in size in order to capture from small to larger files, or some garbage data. For example, some of our test tools generate some random PHP data which are downloaded or uploaded in order to calculate throughput measurements. And the main idea is to place these HTML script tags in a frequently visited website which point to the test tools available in the WiFiMon test server. We are currently using two test tools. The one is called Boomerang, which is supported and developed supported by Akamai, and the other one is called LibreSuite Speed Test, which is a very popular test tool that is has a lot of users, which is also evident from the stars in GitHub. A very important concept in WiFiMon is the placement of the WiFiMon test server. The WiFiMon test server should be placed close to the monitor networks. This is because the round trip time between the end devices and the test server will be included in the results. However, this may be limiting in some situations. However, if it is impossible, WiFiMon will capture the relative performance changes across measurements. The main idea of WiFiMon is not to report that the download throughput is, let's say, 1000 kilobps, but the main idea is to capture relative changes, to see where we have performance drops in order to pinpoint some points in the available charts for the Wi-Fi administrator to take a further look. For example, to see the Wi-Fi configuration if everything is correct. Next slide, please. Okay, the software probes are the end user devices, the devices that, let's say, are used by humans. This could be any Wi-Fi enabled device, a laptop, a mobile phone, a tablet. And these devices trigger crowdsourced measurements, the measurements which are collected from end users roaming the network. The main idea here, the advantage of WiFiMon, is that compared to devices which are placed in fixed points across the network, an end user can be in very strange locations across the network, so it may capture some areas of the Wi-Fi network which may be which may not operating well, which may report bad Wi-Fi performance. And I will repeat that, a very important advantage of WiFiMon is that there is no requirement for additional software within user devices. You can place, you can place the JavaScript lines, the JavaScript script tags in an HTML page, and upon visiting this website, the measurements will be triggered automatically. Of course, you may ask that what happens if I don't want to use this technology? This may be invasive. Of course, someone could opt for some add-ons in their browser which block JavaScript, and WiFiMon will not be used. Next slide, please. The WiFiMon hardware probes are devices that monitor the network from fixed points, and their main idea is to provide baseline throughput to the WiFiMon administrator, so that this can be compared with crowdsourced measurements. The idea is that they use the same technology with the software probes. They use the same test tools, Boomerang and LibreSuite Speed Test, but they also incorporate some additional data about the monitored and the nearby ESSIDs. Recently, we have incorporated T1 measurements, system data, CPU, memory, and metrics from the Wi-Fi network wireless network interface card. Of course, as you understand, these measurements are triggered periodically based on cron tabs. We have currently tested WiFiMon Hardware Probes based on Raspberry Pi devices, version 3 and 4, but any Unix-based device could do the work. Next slide, please. Here is a glimpse from the WiFiMon user interface. You can see that the user interface is friendly to the user. On the left, you can see measurements from a hardware probe per test tool that is used to monitor the Wi-Fi network. And on the right, you can see an average measurement by aggregating the available results. Next slide, please. Apart from various values, WiFiMon user interface also reports other statistics, for example, median, maximum, minimum, and 95th percentile values, because the average may sometimes be misleading. For example, you could see the maximum values and see that the round-trip time reported by a hardware probe is very large compared to the average value. These measurements, of course, could be correlated with the available access points or not, and we're depicting estimations of download throughput, upload throughput, and HTTP ping round trip time. This is not the ICMP ping, but it is a measurement of how long it takes to send an HTTP message and take it back. Next slide, please. Optionally, as I mentioned before, you can correlate the available performance measurements with data from RADIUS and DHCP logs. To that end, we rely on an ELK cluster where RADIUS and DHCP servers, where data from RADIUS and DHCP servers are extracted using FileBit. They are processed and transformed by Logstas in the WiFiMon analysis server, and finally stored in Elasticsearch of the WiFiMon analysis server. You have two correlation options with the end user IP address, which depends only on RADIUS logs, but because this correlation type is mainly based on a RADIUS field that's called framed IP address, which is not always available, we have a second correlation option that is with the end user MAC address. In this case, this MAC address is always available, and in this case, you have to also use DHCP logs apart from RADIUS logs. Of course, a good question here is that what happens with this personally identifiable information, the IP and MAC addresses. Everything is stored hashed in the WiFiMon analysis server, and everything is transmitted encrypted based on the TLS extension of Elasticsearch, of the ELK cluster in general, that is called XPack. Next slide, please. Next slide. Here we will describe the installation process of WiFiMon. You may install WiFiMon using two methods. The first and preferred method is to install WiFiMon on your premises using an Ansible playbook that will install both the WiFiMon analysis server and the WiFiMon test server. In this case, all data stay within the institution premises. In this case, the Ansible playbook we have timed the installation. It takes around 15 minutes. Another solution that is recommended if you want to just try WiFiMon is to use a cloud-based environment that is supported by another GÉANT service that is called NMAS, Network Management as a Service. In this case, only the WiFiMon analysis server installation is possible, and we recommend it only for test purposes. Right now, the preferred method is to use the Ansible playbook. Of course, the manual WiFiMon analysis server installation was abandoned by WiFiMon because it required around 10 hours. Using automated solutions like Ansible, we are now able to install WiFiMon in just 15 minutes. Next slide, please. Next slide. Here is a map of the evolution of WiFiMon. WiFiMon was introduced in 2015. It was first presented at the GÉANT conference that's called Terrain and Working Conference in Porto. Some very successful pilots took place in 2019 and 2020. These pilots are not available in this presentation, but if you search the WiFiMon homepage, you could find very, very nice data demonstrating that WiFiMon was able to capture some very important points related to Wi-Fi network performance in these conference venues. In 2020, after the successful pilot, WiFiMon was declared an official GÉANT service. And we next took steps to cloudify WiFiMon to automate the server components. We also provided support for EduROM by including a JSON exported that streams measurements from hardware probes towards EduROM. And finally, in the next slides, I will show you, next slide please, I will show you some steps that we took in order to automate the configuration and control of WiFiMon hardware probes. Recently, in 2022, we followed the old approach, which had very important limitations. We had some problems operating WiFiMons in NAT networks, and because if a WiFiMon administrator wanted to change something in a hardware probe, for example, to change an IP address, the IP address pointing to the WiFiMon server, the WiFiMon administrator was required to connect physically to the WiFiMon hardware probe, for example, by connecting a keyboard, by connecting a monitor, and this was infeasible for large networks with a lot of probes. Of course, you could enable remote access, but in NAT networks, this was not very straightforward, and WiFiMon administrators should go for some more complex solutions, for example, internal DNS, split DNS, things like that, and we wanted to avoid that. And the final problem was that the administrators were required to edit files manually. For example, they should open the code files, including hundreds of lines, 200 lines or 300 lines, and manually edit some parameters, for example, IP addresses or the monitoring interval, things like that. So we introduced a novel approach that enables remote and user-friendly configuration of probes from a central point. The central point in WiFiMon is the WiFiMon analysis server. And this new solution, this new approach, provides flexibility to control hardware probes, even if they are behind NAT networks. Next slide, please. Here is the configuration that was made easy. This refers to the administrators manually editing code files. Right now, we have a user interface available where they fill the necessary information. For example, an ID for the device, full qualified domain names, or additional information regarding to where the probe is located. And using GÉANT2 templating, everything is transformed into configuration. Next slide, please. The next step is to how we are able to push the configuration into the probes. In order to push the configuration to the probes, we relied on SALT. We relied on SALT because it establishes application layer communication. Recall that contrary to Ansible, which requires SSH, SALT is an agent-based solution which establishes application layer communication. This means that it is mainly based on tokens shared between the SALT master, which in our case is the WiFiMon analysis server, and the SALT minions, which in this case are the hardware probes, and they are able to communicate even if they are behind the NAT, behind a NAT network. So public IP addresses are not required in our configuration, and IP space is conserved. A second very important concept of SALT is that it includes a built-in 0MQ message broker. This message broker enables parallel configuration regardless of the hardware probe number. For example, theoretically, if you have a limited number of probes or a lot of probes, the configuration should be pushed in around the same time. And finally, we rely on SALT to push the configuration files from the WiFiMon analysis server to the hardware probes. Next slide, please. So this was my presentation. Thank you. You may visit the website of WiFiMon, which is depicted here in the home page. And we would be delighted if you contact us in the WiFiMon mailing list in order to help you and guide you to install WiFiMon, mainly using the Ansible playbook. Thank you.